lecture. So this is the extrinsic semiconductor, N-type or the P-type doping. So once we dope the semiconductor with dopants, we are going to shift the Fermi level towards the EC or EV, depending on the type of doping. So if it's N-type doping, then the EF, the Fermi level, will be close to the conduction band edge, EC. So if it's P-type doping, then the EF is closer to the valence band edge, EV. And then we have the example on this question. So here we ask where is the EF if we have a P-type dopant density like Na equals to 10^17. So this is a very typical question, and you have seen this in your homework 1. By the way, so the homework 1 is due tomorrow midnight, and please make a PDF and then upload to the Canvas system before the deadline. We don't accept the late submission. So any questions? And in here, this is the way we approach this question. So we use the equation for the whole density in this case, and then we take the log on both sides. Then you can get the EV minus EF, which is the distance between the Fermi level and the valence band edge. So this is determined by the doping density, and then you can get the EV minus EF, this one, in this case, 0.119 electron volts. And then for the minority carrier density here, N, because this is P-type, so the electron density N will be the minority carrier. Then you can always use the NP product for this kind of a question, because the NP product will be a constant regardless of your doping. Then here the NP product is Ni squared. Ni is the intrinsic carrier density. So you can use this for the minority carrier density N, and you can do this way. So this is the lecture 5. And then we started with lecture 6, which is on the carrier transport. As I said, lecture 5 is on the carrier statistics. That means the density of the carrier is the electron or hole. And lecture 6 is on the transport of the carrier. That is how fast the electron or hole will move in the semiconductor. So the first mechanism for the carrier transport is this drift. As we discussed, drift is when you have the external electric field. The electrons will move opposite to the field, and the hole will move along the field. So this is purely field-driven. And then we will have the concept of mobility. So this is similar as lecture 2 when we talk about the metal interconnect. So there we only have the electron. So we only have the electron mobility. But here in the semiconductor, we have both electron and hole mobilities. And the velocity of your carrier, no matter electron or hole, then the velocity is proportional to the electric field. And then the coefficient is this mobility. So mobility essentially describes how fast your carrier will move under the electric field. And here the important conclusion is that the electron mobility is higher than the hole mobility in most of the semiconductors, including the silicon. So here are typical numbers for the electron and hole mobility. This is without doping. This is for intrinsic case. Because as we see later, with the doping, so this mobility number will decrease because of what? We talk about that last lecture. If we increase the doping, then this mobility number will drop because scattering. Right? We talk about this scattering. So with the doping, then you are going to introduce those negative or positive charge center. For example, the boron will be negative charged in the nuclei of boron, or the arsenic will be positively charged in the nuclei of the arsenic. Then those will be the scattering center for the electron or holes. So then it will slow down the velocity of electron or hole. Then it's like a decrease of the mobility. So here is the measured data for the mobility as a function of the doping density for electron and hole in silicon. So you see the degradation of the mobility as we increase the doping density. And then if you consider this drift current, then we will have this equation here for the electron or hole current density. So it's Q, which is the charge quantity, and N is the density of electron, or P, density of the hole, and then the velocity. So essentially, as I said, for the current, you think about two factors to determine the current density. One is how many carrier electron or hole there, so that is the N or P, and then how fast they move, then that is the velocity V there. So you will have those in this equation. So this is the drift current. We need to consider both electron and hole, and then if you do that, then you get this one, and then you can define the conductivity as this Qn mu n plus Qp mu p. But in practice, because your semiconductor is either N type or P type, so you can ignore the other one. Because here only the majority carrier will dominate the current. So in practice, you can ignore the other one.
Are we using the on centimeters or on meters?
So I think in this semiconductor field, centimeter is the typical unit. So all the length is on centimeter. I don't know why. Don't ask me why they use centimeter, but that's alone in this field. So yeah, let's just follow that. Okay, so this is the drift current. And then here is another chart shows the relationship between the doping density and the resistivity of the silicon. So you know the doping density will determine the mobility, and then from the mobility you can get the conductivity or resistivity, right? So you can also refer to the previous chart here. So this is experimentally measured the mobility as a function of dopant density. So you will get the mobility as a function of those N or P. And then you can use this equation to determine the sigma, which is conductivity, and 1 over sigma is the resistivity. Then you can get this resistivity and then the doping density function. So as you can see here, the typical doping density, as we discussed, is like 10 to the power 15 to 8 times 10 to the power 18, so roughly is here. This is 18. So this is the range of the practical doping density in the silicon. And then within that range, you can see the resistivity change from here to roughly here. So this is 10 to minus 2 to 10 ohm centimeter. So you can see there are like 3 orders of magnitude change in the resistivity. And by tuning the dopant density, you can tune the resistivity of the silicon. Of course, the higher doping density, then the lower resistivity. So this is some practical relationship. And you will also notice N-type doping will have lower resistivity. This is because, as we discussed, electrons have higher mobility than the hole. So the N-type silicon will be more conductive. That means less resistivity here. Okay. So then here, this is a simple example to determine the resistance of the doped silicon. So here the question is, what is the resistivity of the silicon with this kind of doping density, 10 to the power 17 for the arsenic? And here you know arsenic is N-type doping. So what we can do here is to use the previous chart here. We can determine the resistivity from the doping density here, 10 to the power 17. So it's this one. And you look at N-type curve here, so it's roughly here. And then you look at the resistivity somewhere here below the 10 to -1. So if you do it carefully, then this is the number, 0.084 ohm centimeter. So this is from the previous slide, that figure. And if we have this kind of resistivity, then it asks if we build a piece of silicon with 1 micrometer long and 0.1 micrometer square in the cross-sectional area. So what is the resistance? So essentially it asks if we have a piece of silicon like this, and the L is 1 micrometer, and then the cross-sectional area 0.1 micrometer square. Then what is the resistance of this silicon? So this one you can apply that simple resistor equation. You maybe have learned this from high school, and also we derived this from very beginning, at the lecture 2, I think. So this R resistance equals to resistivity multiplied by the length L divided by the cross-sectional area A. So of course, the longer the silicon is, then the larger resistance. Or the larger cross-sectional area is, the smaller the resistance is. So then you plug in the numbers here, but you need to convert the units. This is always you need to do in this kind of question. Then like centimeter, micrometer, so you need to convert the units. And then if you do that, then you can get this number. It's 8.4 times 10 to the power -4 ohm. So it's very small resistance. So that's why sometimes if we dope the silicon heavily, this one is not even heavily doped, 10 to the power 17. It's the kind of high doping, but not the very high, because you can do up to like 5 times 8, 10 to the power 18. So if you do this heavily doping, then you can use this as interconnect, local interconnect, as we discussed before. So for some short distance on the chip, then you can use the doped silicon as your interconnect. And for example here, the MOSFET, as we see later, the transistor's gate can be the doped polycrystalline silicon as the gate electrode. Question?
I think the final answer is 10 to the 4, not 10 to the -4.
You mean the final answer?
Yeah.
The order of magnitude is wrong?
I'm not sure. I think based on the equation there, it's 8.4 times 10 to the 4 instead of -4.
So here, I think it should be correct because I copied from the textbook. So, but we can do it, right?
Resistance sounds really low.
This is a -6, right? And then if you move to, then it's -4, right?
You're
That's
dividing
positive
and
6.
Uh-huh. So you mean it's you divide, then you get a 10 to. You mean it should be +4?
Yeah.
This should be +4. Yes. Yeah, it's net +4 to me. So it seems net +4 to me, but this slide I just copied from the textbook. So I didn't even change anything. You see the bottom line is the title of the textbook, and this slide is from the appendix of that textbook. It has some lecture resources. You can have the slides there. So yeah, I can double check after this. All right, so let's start the discussion on another topic here. There are another kind of mechanism for the carriers to move in the semiconductor. We talked about the drift before. That is due to the electric field, because electrons and holes are charged, so it can move under the electric field. But there is another mechanism for the carrier to move. That is called the diffusion here. So what does this mean? So that means in the semiconductor, if your carrier concentration is non-uniform, so for example, here in the left-hand side, if you have a higher particle, let's say electron or hole concentration, on the right-hand side, you have lower particle, for example, electron or hole concentration, then you will have this kind of diffusion. You know, those particles tend to diffuse from higher concentration to the lower concentration. So then this kind of mechanism is called diffusion. And the direction of the diffusion is always higher, from the higher concentration to the lower concentration. This is due to the thermodynamics. You know, they want to be stabilized. So you can think about this is like an electron. Those are electrons. Then the electron will tend to move in this direction. Then of course you will have current flow to the left. So this is called diffusion. And then we can define the diffusion current, because this kind of electron or hole flow will also contribute to your current. And then we can define the current density. That is the current across the unit area. So the diffusion current density is defined as this way. So Q, of course, is the charge quantity. And then here we have a coefficient, dN or dP. That is called the diffusion constant for electron or for hole. And then we have this term. This is the derivative of the electron density respect to the, let's say, for example, if you consider one-dimensional diffusion, then it's respect to the x direction. For example, here we have this electron density, which is non-uniform along the x direction. So if we have this kind of profile, here we have higher concentration, that means we have more electrons. more electrons. So here we have less electrons. So if we have this kind of profile for the density of the electron, then as we discussed, the electron tend to move this way. So if electron tend to move this way, then here the current flow by definition is to the right. And here we want to say that the current density is proportional to the slope of this gradient, or let's say gradient of this electron density respect to the x. That means you take the derivative of n with respect to x. That means dn over dx. So that means the slope will determine the slope is dn over dx. So you can imagine that if you have another kind of profile like this, then you have another dn dx. So this one, the top one, will be larger than the bottom one in terms of the gradient here. That means you will have larger currents for the top case than the lower case.
Can you repeat that last part? Can you repeat that last part?
So if we assume there are two kinds of profile of the current of the electron density, those two cases, if we want to compare the current density of those two cases, we will need to look at the slope or the gradient of this profile. Then the top one will have larger gradient here than the lower case. So this one will have larger current than the lower one. And here, one more thing is the, let's say this is essentially positive sign in front of the Q. The reason is that you can see here the gradient of this one is positive. If you look at this profile, this gradient here is positive, and then here the current flow is to the right. So then current flow is positive. So that's why we have positive sign here. This is a little bit different when you consider the hole diffusion. The left one is electron, and the right one here is a hole. If it has the same kind of profile, but then we need to take the negative sign here. The reason is still the gradient is positive. The dp over dx is positive. But since the hole will also move the same direction, so the current will also move to the left. That means current is negative. So that's why you need to have a negative sign here for the hole diffusion. This is purely by definition because of the electron hole flow direction is different. So any questions here? So this dn and dp is purely the coefficient for this.